So hi again everybody. In the last video I talked about the digit recognizer, and I also explained how our neural network is going to work. And in this video we're going to implement the matrix and all the operations we need. And also we're going to implement a simple pseudo random number generator. So let's start. Just some header stuff here. Okay, let's start with the pseudo random number generator. I'm going to use XOR shift. It's basically a family of pseudo random number generators. This one in particular was called XOR 128 as far as I remember. You can Google it. Don't get confused. All you gotta know about it is that it's very good at generating pseudo random numbers. I have to type in some random numbers here. Doesn't matter what I type. Okay, let's go this way. Oh. Oh. Okay, so this is pretty much the XOR shift random number generator. And I also want to have a function run01, which will generate a random number between 0 and 1. And the way I'm going to do this is by first generating a random number between 0 and 10 to the 9th power, and then dividing that by 10 to the 9th power. Okay, this should be good enough, and this is all about the random number generator. Now we can go on and start coding the matrix. So n and m will be the number of rows and columns respectively, and I have a two-dimensional double array. Now let's have some constructors here. The default constructor being an empty matrix. Now here we create a matrix with the given number of rows and columns, and also set all elements in it to 0. So n equals rows, m equals cols. I also want to have I and j. Okay, now let's go the C++ way. And set each element to 0. Okay, and one last constructor which will construct the matrix from a given one. So just copy the number of rows and the number of columns. And copy each element. Copy every element, I'm sorry. Okay, now I want to have an assign operator, which will do pretty much the same thing. Okay, so I will just copy that. Let's see if this will compile. Why is it taking so much time? Yeah, it compiles. Now we also want to have a destructor which will free the memory. So we simply go through each row, delete that row, and then delete the whole matrix. Okay, now a member function randomize, which will assign random numbers between -1 and 1. And the way we're going to do this is the following. We first take a random number between 0 and 1. That's the function we already implemented. And then we randomly assign a sign in front of it. So if a random number between 0 and 1 is 0, a random integer, then we put a minus sign in front of the current number. Now also a function 0, which will set everything to 0. So that's it. And I also want to have one last function, add, which simply takes a matrix X, and we assume that X has the same dimensions, I prefer saying dimensions, I know both are correct. So we're simply going to add each element of X to the corresponding element of our current matrix. You'll see why we're going to use that in the future. Basically, the reason is that the neural network is going to be trained on mini batches, and for those mini batches we're going to accumulate some gradients, delta values, and then after that we're going to divide those delta values by the size of the mini batch. So that's why we need to have an add function which helps us accumulate some values in a matrix. And one last thing I want to have in the matrix is a square bracket operator, which will help us access the matrix elements. It simply returns a reference to the corresponding element. The reason I'm doing this is, okay, say I have matrix D, and I don't want to write d.aij, and with this operator I can simply use dij. That's why. Let's see if this will compile and we can go on. Perfect. So now we want to have a add function, once again an add function, sorry, which will simply add those two matrices and will return the result. Term by term addition, of course, we assume A and B have the same dimensions, once again, dimensions. Pretty simple stuff. And then return the answer. I also want to have the same thing but for subtraction. So I'm gonna copy that, subtract, replace the plus with a minus. And also, once again, but for multiplication, and I cannot name that multiply because that's not the matrix multiplication, that's just term by term multiplication, and I'm gonna name that term by term. There was a name for this kind of multiplication, which I do not remember, but as far as I remember there were actually two ways, at least two ways to call this, but I don't want to Google that now. So let's compile again. Very nice. So next thing we want to have is the transpose operations. Transpose operation. Pretty much it just takes the first row of the matrix and flips it by 90 degrees, rotates it, I'm sorry, not flipping but rotating by 90 degrees, and makes that the first column of the resulting matrix. Then we take the second row, rotate it, and make it the second column of the resulting matrix. That's simple. Simply the rows become columns. Okay. Don't forget to inverse the rows and the columns. As simple as that. And now the multiplication. I'm assuming you know how the matrix multiplication works. It will have the result will have the number of rows of A and the number of columns of B. So I'm simply looping through all elements of that matrix, of the resulting matrix, and I'm just going to accumulate those products. Oops. Notice that I don't have to set ans ij to 0 before that, since the constructor takes care of that. We made it work this way. And now one last thing, we want to implement the sigmoid and the sigmoid derivative function. The sigmoid, as I said, is 1 divided by 1 plus e to the power of minus x. This x function, if you don't know, is simply e to the power of something. Now the sigmoid derivative, I'm assuming x is already the sigmoid. I don't want to, like, x is not just a number we want to take the sigmoid function at. X is actually the sigmoid function for some value, so the derivative is simply x times 1 minus x, as I said in the previous video. Proving this is simple, you can Google it always. Now I want to have the same operations, the same functions, but for whole matrices. So we simply want to go through all elements of A, apply the sigmoid function, and get the result. Okay. Oh. And the same thing for the sigmoid derivative. I'm just going to copy that. Oh. Yeah, it works, and so that's for this video.